Okay, so now we're going to relate our gas laws to we're going to look at the molecular level. What's happening at the molecular level to explain these gas laws? What's happening? So the kinetic theory of an ideal gas, of course, theories are things we don't know them absolutely, but they hold up over time. And so a theory is just something that you create to explain something. So the ideal gas law, we know how the gases behave, but we don't know exactly why it's behaving that way. So we're going to make a model called the kinetic molecular theory, and hopefully this will explain what's happening to the gases. So the kinetic molecular theory will make a few assumptions. We're going to assume that gases consist of large numbers of atoms or molecules that are in continuous random motion. We're going to assume that the volume, if you took all the molecules and squished them together, that they would take up a very small part of the volume. So we're assuming that the volume of the molecules is negligible compared to the total volume that the gas is contained. So this may not be true, but we're making that assumption that we can ignore the volume of the actual molecules themselves. They don't take up much space. That most of it's empty air. We're also going to assume that there are no attractive or repulsive forces between molecules, or if they're there, they're very negligible, and that's going to be important. So meaning they're ignoring each other. They're all just moving around ignoring each other. We also have to assume that energy can be transferred between molecules during a collision. So if two molecules hit each other, they can collide and energy can be transferred. But keep in mind that energy is not going to be lost. It's going to be transferred evenly. So the average kinetic energy of the molecules will not change as long as the temperature changes, because they're directly related. So as long as the temperature remains the same, the overall energy of the molecules will be the same, and they can transfer it from one to another, but we're not going to lose any energy overall. And then finally, like I just said a minute ago, the average kinetic energy of the molecules is proportional to the absolute temperature. So in other words, on average, if you're at low temperatures, molecules move slower. At higher temperatures, molecules move faster. So at any given temperature, the molecules of all gases will have the same kinetic energy. It doesn't matter what the identity is, they'll have the same kinetic energy. Remember, I said earlier that it's helpful to imagine that the pressure of a gas is caused by collisions of the molecules with the walls of the container. So as the molecules hit the container, they're creating a pressure, and that's an easy way to kind of visualize this and to explain it. So the amount of pressure will be determined by how often and how forcefully molecules hit the walls of the container. Now we said that temperature is related to the kinetic energy, and so the temperature is a measure of the kinetic energy. And of course, if we're at absolute zero, then there's no molecular motion at all. As the temperature increases, the molecular movement increases. So the important thing to remember is that if you have two gases at the same temperature, they will have molecules with the same amount of kinetic energy. That doesn't necessarily mean they're moving at the same speed, but they have the same amount of kinetic energy. If we increase the temperature, the kinetic energy will increase. And so that means molecular motion will increase with increasing temperature. And I'll tell you in a minute what I mean by it. Like, we could have two different gases that are at different speeds, but they can have the same kinetic energy. All right, so let's see how this applies to Boyle's law. We know Boyle's law says pressure is inversely proportional to volume. Well, and temperature staying the same. So remember, if temperature stays the same, that means the molecules don't speed up or slow down. They have the same speed all the time. So if we increase the volume, if we make the volume of the gas of the container bigger, what happens? Well, the molecules have to move a little bit farther to hit the walls. So in other words, the molecules will hit the walls less often. If they hit the walls less often and less forcefully, that means that pressure will decrease. So there will be fewer collisions per unit time with the containers and pressure decreases. So we increase the volume, the molecules have to move farther to hit the walls, so they will hit the walls less often and less hard, and the pressure will decrease. Of course, the opposite of that is true. If we decrease the volume, that means we make the area inside the container much smaller. Now the molecules will hit the walls more often, and so the pressure will increase. So that's the inverse relationship. What about Charles's law? Remember that temperature is directly proportional to volume at constant pressure. So remember, pressure is staying constant. What does that mean? That means we don't want the molecules to hit the walls any more often than they are doing. They have to have a constant number of collisions with the wall. So what happens if we increase the temperature? If we increase the temperature, all the molecules are moving faster, right? So if we don't do anything to the volume, the pressure will increase, because and that's actually the next law. I should reverse them because that makes more sense. But so they're moving faster, and if we don't want the pressure to change, in other words, we don't want them to hit the walls more often, we're going to have to increase the volume. We're going to have to make the space bigger so that they don't hit the walls any more often than they did at the lower temperature. So if we want pressure to stay constant, volume must increase so that the number of collisions stay the same. So that's Charles's law. And of course, if we decrease the temperature, but we want the collisions to be the same, then we have to make the volume smaller, because then they can hit the same amount. So temperature and volume are directly related. And then of course, Guy-Lussac's law, I just kind of alluded to it. Temperature is directly proportional to pressure. So again, if we increase the temperature, but the volume doesn't change, because the molecules are moving faster, because of the temperature increase, molecules are moving faster. They hit the walls more often. They actually hit with more force too, because they're moving harder. They're going to run into those walls. So they're hitting more often and with harder momentum, more momentum, and so pressure increases. So this is something I would like you to be able to answer, just, using the kinetic molecular theory, explain what's happening in a container if temperature increases, what happens to volume, so forth. So just keep these things in mind. So again, although the molecules have the same average kinetic energy, so kinetic energy depends on temperature, that doesn't mean every single molecule inside that sample is moving the same speed. Individual molecules can move at varying speeds, but the average, remember, kinetic energy is related to the average speed. So molecules actually at any instant have a wide range of speeds. Of course, at higher temperatures, there's more of them moving at a faster speed. And so the kinetic energy increases, but still, at any particular time, different molecules will be moving at a different speed. So if you look at this graph, it kind of makes sense. So you can see here at 100 degrees Kelvin, very low temperatures, let me change that color, very low temperatures, most of the molecules, so the average will be at the top of the peak. The average kinetic energy at 100 degrees Kelvin is about 250 meters per second. If we increase the temperature, we're not saying all molecules move at 250. So you can see, let's stay with 100, you can see that many of them are going slower than 250, and there are some that go higher than 250, but the average is 250. But you can see that if we increase the temperature now to 200, which is this line, you can see that all molecules are moving faster. There's still some moving very slow, but now there's more of them moving faster under here, and the average has increased. So now it might be about 350. If we increase to 500 degrees Kelvin, you can see that, again, the average has gone up to maybe 600. And now we have a whole lot going very fast. We still have a few going slow, but many fewer than we did at lower temperatures. So, but again, the average. And then finally, if we raise it to 1,000 Kelvin, you can see the average is maybe up here at maybe 800 meters per second. And we have a whole lot moving very fast, way more moving faster than, like here, there's really none moving it greater than maybe 700, whereas there's more and more. So as you increase the temperature, the average speed increases and more of them are moving faster, but it doesn't mean every single one of them are moving faster. So we can look at a definition. So U is just a form of average molecular speed. So we're just going to use that as our variable for average molecular speed. It's actually inversely related to molecular weight. So we don't need to worry about this, but it's inversely related to the square root of molecular weight or molar mass. And so don't worry about this so much, but I just want you to see that they're inversely related. What does that mean? The heavier the molecule, the slower it's going to go. The smaller the molecule, the faster it will go. They're inversely related. So if we're at the same temperature, their average kinetic energy depends on mass and speed. Kinetic energy equals 1/2, if you ever remember kinetic energy, 1/2 mu squared, or mv. V is velocity. Sometimes you may have seen kinetic energy is 1/2 mass volume, or mass times velocity squared. It's the mass, so kinetic energy depends on the mass and it depends on the speed. If you have two small cars going, one going fast and one going slow, the one that's going faster has the more kinetic energy. But if you have like a small car and a truck, and they're both going the same speed, still the truck has more kinetic energy because it's bigger. So kinetic energy depends on mass and it depends on speed. So if we have the same temperature, then we know that we have the same kinetic energy, that the total energy. However, smaller molecules will be moving faster and heavier molecules will be moving slower. So they have the same kinetic energy, but because it depends both on mass and speed and mass, both kinetic energy depends both on mass and speed. What we do know is that since the molecular mass of helium is smaller than xenon, then the particles of the lighter molecule will move faster, even if they have the same kinetic energy. So this is another picture. So this one looks similar to the last one where it's speed on the x-axis, but now this is just probability density is sort of a way of just saying how many are at this case. So you can see here xenon, which has the most mass. Actually, most of the molecules here are moving. The average speed is about 200 meters per second. And some are moving slower, some are moving faster, but the average is about 200. The argon, which weighs 40, so it's much lighter, you can see that the average is about 350. Neon, which has a mass of 20, has a speed of about 50, an average speed of about 50. And then helium, which only weighs 4, looks like it has a speed. So the mass and the mass of the molecule will also determine how fast it's going. They all have the same kinetic energy because we're all at the same temperature. However, slower molecules will move slower than faster molecules. I'm sorry, smaller molecules will move faster than bigger molecules at the same temperature. Now, what effect does this have on a couple of characteristics of gases? So effusion is the definition, is the transfer of a gas through a membrane or orifice. So what you're seeing here is that these gas molecules are moving through this little hole here into the other container. That's called effusion. So since we know that heavier molecules move slower, then we can also say, and this is our formula, this is called Graham's law. So if we remember we said that that the speed that U is inversely related to molecular mass. So if we put this all together, we get Graham's law. It says that the rate of effusion of gas A compared to the rate of effusion of gas B is actually equal to the square root of the molecular weight of B divided by the molecular weight of A. So again, the heavier the molecule, the slower it will effuse. And we can actually do a calculation to figure out how much faster is one gas over the other. So again, lighter molecules moving faster, they're more likely to effuse or escape through a hole. And that just is common sense. So we can actually do a calculation. How much faster would hydrogen gas effuse through an opening than methane? So we say the rate of effusion for hydrogen divided by the rate of effusion for methane is equal to the inverse of the molecular weights. CH4, the square root of the inverse. CH4 weighs 16, hydrogen weighs 2, so the square root of 16 divided by 2 is 2.8. So it turns out that hydrogen will effuse 2.8 times faster than methane. If you look at this photograph, the left photograph shows two balloons with different gases. They're telling you that helium is in the orange balloon and argon is in the blue balloon. Argon is heavier than helium. So after about 12 hours, they're kind of open into a test tube. So the gas is able to effuse down into something else. So after time, you can see that the helium has more of the helium has effused than the argon. That's because helium is faster at effusing than argon. Now, diffusion is a slightly different idea. Diffusion is just the spread of one gas throughout a space or through another gas over time. So there's no little orifice here. Diffusion actually follows an approximation of Graham's law as well. So it sort of makes sense. A faster, lighter molecule will diffuse quicker. A heavier molecule will be moving faster and will diffuse slower. Diffusion's a little harder because what's happening is some of these gas molecules might hit into other gas molecules, so it may impede their speed. So it's not quite as clear of a relationship, but it's still reasonable. Okay. So the last thing we need to talk about is non-ideal gases. Gas behavior is often non-ideal. We've been talking about these ideal gases and how they work perfectly, but some gases don't work quite as well as we'd like to think or we'd like them to. So we can actually get a measure of how close to ideal a gas is by looking at what's called the compressibility factor, or Z. And what this is just the actual volume of a gas at standard temperature and pressure divided by what would be ideal at standard temperature and pressure. So it's just a measure of how off from ideal we really are. Of course, the further away from Z from 1 that Z is, the less ideal. So if the actual and the ideal are the same, then Z will equal 1. That means that the actual is working very ideally. And so the further away from 1 this ratio is, then the less ideal that gas is. Here's a graph of compressibility factor, and it shows, so this blue line right here is ideal, and they're showing you that nitrogen at low pressures is not too far from ideal. And then as you get increasing pressure, it gets far away from ideal. Methane is much less ideal. It gets further away from 1. Oxygen also not so ideal. Looks like hydrogen, not really. It just keeps going up and up and up. So anyway, so not all gases work perfectly, although in general, the ideas that we've talked about hold. So actually, and there's actually a very complicated formula that can correct for non-ideal gases. So if real gases don't follow PV equals nRT, this van der Waals equation actually corrects for those things, and it corrects for two things. So let's look at them in this. I know it looks kind of complicated, but again, there's nothing new here except two new values, A and B, but we still have volume, we have pressure. So we're correcting pressure and we're correcting volume, and then it equals nRT. So this overall pressure times this overall volume. So A, this little value A, actually corrects for interactions between atoms. So remember our original kinetic molecular theory said, oh, molecules ignore each other. They're not attracted to each other. But it turns out that non-ideal gases are attracted to each other. So this actually corrects for that attraction between or interaction between molecules. And then B actually corrects for volume. So the other thing we said in the kinetic molecular theory was that that if the molecules take up negligible space, well, that's mostly true, especially at large volumes, but if you have smaller volumes or higher pressures, then the molecules themselves may take up more space than more than what can be considered negligible, and so we have to correct for that. So again, the V part becomes V minus NB. So B is actually a constant that you can look up depending on the gas. And of course, N has to do with the number of moles. So that would probably be given to you in the problem. So here's what I was saying. So, here our volume is, the volume of the actual molecules is negligible because they're a very small portion of the total volume. But maybe at lower volumes or higher pressures, the molecules themselves actually take up more space than you would expect. So, so we have to, so depending on the gas involved, we have to correct. And then, like I said here, P becomes P plus N squared A over V squared. So of course, N squared is the moles squared. A is a value that corrects for intermolecular attractions. And so here, ideal gas, they're all ignoring each other and wandering around the space without interacting. However, in a real gas, some of the molecules are attracted to each other. And so the pressure changes a little bit because of this interaction. So like I said, you can look up, if you're talking about CO2, you can look up what is the value for A, 3.658. What's the value for B? So these numbers are just something to look up. It's not easy to solve the problem, but it's not difficult to conceive. So you can, depending on the gas, you can pick the correct. So let's just look at an example really quick. Sulfur dioxide, if it were an ideal gas, the pressure at 0 degrees Celsius by 1 mole, the pressure at 0 degrees Celsius exerted by 1 mole occupying 22.4 liters would be 1 atmosphere. That would be standard pressure. But using the van der Waals equation, let's estimate what the real pressure is. So if we look up the values on the previous chart for SO2, we find out that A is 6.865 and B, and these funky units, and the units are there just to cancel out so that the units will all work out. And then 0.05679 liters per mole for B. Now, let's just talk about this for a second. So we had P, let's write it over here. So we had P plus N squared A over V squared times V minus NB equals nRT. So if we're solving for P, see what happened? We actually divide both sides by V. So we had this, P plus N squared A over V squared equals nRT divided by this quantity. And then if we just want to solve for P over here, then we subtract N squared A over V squared. You didn't know you were going to get an algebra lesson. So if we subtract that from both sides, then we have this. This is a rearrangement of that equation. Now, on the previous slide, they're telling us it's 1 mole R, of course, is the constant. They're telling us the temperature is 273, 0 degrees Celsius, 273 Kelvin. We know what R is. Let me erase this so you can read that. So we know what R is. We know what T is. We know the volume. 1 molar volume is 22.4 liters. We know what A is. We know what B is, and we know that we're talking about 1 mole. So you're just plugging those numbers in for these values, for these unknowns here. So if you plug all those numbers in and do all that crazy math and all the units, like I said, all the units will cancel. Kelvin, moles will cancel, and then we have liters that will cancel, and liters here, liters will end up canceling with that, and then our unit will be atmospheres, which is pressure. And then again, we have moles squared will cancel. You don't have to worry about this. Liters squared are canceling, and again, atmosphere, so we're going to have atmosphere minus atmosphere gives us atmosphere, and you can see that the pressure of 1 mole of SO2 at standard temperature pressure is a little bit lower than 1 atmosphere. Not standard, so at standard temperature and standard volume, 22.4 liters, the pressure will be a little bit less than 1 atmosphere. So you can actually do some calculations. Now, I will tell you that there won't be anything like this on the test. I do want you to know what we're correcting for, the interactions and the volume, but I'm not going to have you do any of these kind of calculations. So, I want you to be able to do at the end of this chapter. You should be able to define pressure. You should be able to convert units of pressure, millimeters of mercury, torr, atmospheres, probably not PSI, but you could if you were given the conversion. Be able to use the empirical gas laws, Boyle's law, Charles's law, Gay-Lussac's law. Be able to also use the combined gas law, which is all 3 of them. Then be able to use the ideal gas law, so being able to use these 2 gas laws to solve various problems. Be able to relate density and molecular weight, so using that equation where density and molecular weight are involved. Be able to solve stoichiometry problems involving gases, so being able to find the moles of a gas and then convert it to moles of something else and figuring out how much of something else you need. Be able to state Dalton's law of partial pressures and be able to use it in simple calculations, which isn't anything more than what you saw in this video. And then define and explain effusion and diffusion, and be able to use Graham's law to compute the ratio of effusion. Also, just kind of in general, know how effusion and diffusion will depend on the mass, molecular weight. And then finally, know the kinetic molecular theory, be able to state those postulates. Use the kinetic molecular theory's postulates to explain the gas laws, being able to, so you know, I'm not just saying, oh, well, the pressure went up, so the temperature goes up. What are the molecules actually doing? Well, if the pressure goes up, that means they're hitting the walls more often, so that can only happen if they move faster, which means the temperature goes up. So that kind of thing. What's happening to the molecules? Be able to describe the factors that lead to deviations from ideal gas law. So again, not having to do that calculation, but knowing what those 2 factors are: the negligible volume, non-negligible volume, and the attractions. Define compressibility, the compressibility Z, and describe how its variation reflects non-ideal behavior. And then actually I have here quantify non-ideal behavior by comparing computations of gas properties, but there's not likely there won't be anything like that on the test. So just knowing what it is that lead to deviations. And that's it. So thank you for joining us.